Yeah, I'm just.
You also don't have to have a countdown. You can just count down 5 minutes and switch.
It's my fault.
Well, I always have to get like in my box here. I'm always just kind of like half like this, you know. So, well, hello everybody. This is Scott Roberts with Explore Scientific and the Explore Alliance, and this is our 48th. No, it's our
49th.
49th.
49.
How do you know program? and it's about the Hubble constant mysteries, or the mystery of the Hubble constant. And there's so much. I mean, the more I just kind of read, I mean, you had to teach the Hubble constant. I'm like an armchair Hubble constant kind of guy. Okay, and so. But trying to explain the shape of the universe, and how it's bucking up against Einstein's theories of what was that really famous one, relativity. Okay.
Yeah,
um, that's where things start to get really interesting, and I'm sure that's part of the
they do.
mystery of the Hubble constant. So I'll turn it over to you, Daniel. Thanks for bringing on yet another great episode.
Hey, well, thanks, Scott. I love these kind of episodes where we get to go deep and take a two-parter and really dig into some of these fundamental mysteries of the universe. And I know there's a lot of skim journalism. If you go and you put into your search engine Hubble Constant Mystery, you get three levels. You get the complete gobbledygook, where it's clear the person who's been given the assignment to write this has no idea what they're reading about or reporting on. And you're just like, that's not right. And you see outright mistakes and silliness. Then there's the skim level. This is sometimes a level that NASA, ESA, and university professors, not pointing any fingers, somebody says, give me a 5 minute thesis on the Hubble constant. And you're like, okay, this is just like the tell me what you can tell me in an elevator ride from here to there. Then you dig a little deeper and you find some videos and some papers and some things written by people who are really principal investigators in this area. They're helping plan and conduct the research. They're writing the proposals for time on the Webb telescope and Hubble, and they're already busy planning what they can do with the Roman space telescope when it gets up. And these people go in, and what's interesting is there's this tremendous gap between the two. The people who are really living it every day, they their daily conversations are with people who are steeped in this literally to the eyebrows. And they make a lot of assumptions about their stuff we all know, right? And you have to stop and say, but how do we know? How do we know this? I love to be able, this program gives me a platform, and Explore Scientific and Explore Alliance gives me a platform to bridge that gap between the first order level where you have one research scientist talking to another and the best sort of skim presentations on topics that come up. Because the stuff that NASA, ESA, and many other people do is very good, but it's watered down a lot because the topics are too complex to present in a 4 minute video or in a 2 minute read, right? You go through and you see something on your feed and says 2 minute read. Oh, good. I can get through this. I can understand it.
Right.
Well, we're going to dive a little deeper, Scott. We're going to jump into the deep end a little bit, and I will be your guide. So we're
Awesome.
going to get
Well,
going.
how many years has it been since Hubble first posited the Hubble constant? Has it been 100
Oh
years?
gosh,
Not quite.
Hubble getting close. He published his paper on expansion, and that led to Hubble. And that was in 1929. It's
Okay.
been 100 years of research because he started in 1920 or thereabouts, right after World War I ended, and he got his position, and the 100-inch Hooker telescope came online, and he had the freedom to say, "I want to explore this." So we've had 100 years of research. It's not been 100 years since the idea of the Hubble constant was proposed. Really, Hubble himself said the universe is expanding. It's other people who uh, took the baton from there, if you will, and ran ahead and said, well, how fast is it expanding? Is it the same everywhere? Has it always been the same through the history of the cosmos? And a great deal of that was problematic. And
Mm.
one of the problems is that although the Hubble constant is one of the fundamental values of the universe, there are things like the gravitational constant, the fine constant, the charge on the electron. And if you change them just a little bit, our universe changes drastically. Hubble constant is one of these most fundamental things. It helps us understand how big is the universe, how old is the universe, what's the shape of the universe. We'll talk more about that as we dive in. Uh, and we originally thought it would be very simple. The universe would be open, closed, or flat. So an open universe, gravity loses, and the Big Bang is big enough that everything expands forever. And a closed universe has the Big Bang, and then it comes together again, and you have the Big Crunch, and the universe goes bang, crunch, bang, crunch, bang, crunch. And that's a very nice idea because the universe is essentially infinite in time, and we don't have to look forward to something that gives us stress like the heat death of the universe. The other thing is the flat universe, which says it's exactly right, so that it keeps slowing down, but it never stops. It's an
Mm.
asymptotic universe. And it turns out none of those ideas are complex enough to actually deal with reality as we understand it. And so the other issue that we must understand as we go in, the Hubble constant, unlike the charge of the electron, unlike the fine constant, unlike the speed of light, these are things we can measure in the laboratory. Romer did the first estimation of the speed of light working with the satellites of Jupiter, and other people refined that through the years, and we now have a very good idea. And you can actually, I've seen an experiment done. This is a wonderful one. You take you make a cookie sheet of chocolate and you carve it up so that it just fits the round pan in your microwave, and you turn on your microwave on high until you get some melted spots, and from the melted spots you get the wavelength of the microwaves, and from there you can calculate the speed of light. It's a brilliant kitchen
Oh,
experiment. It's
wow.
really,
Yeah. We'll have to see
but we can
that played
we
out.
can do these experiments, whether you're talking crude at home lab or you're talking about fancy equipment at a major laboratory. We can measure them directly. The problem with the Hubble constant is we can't do that, Scott. We're talking about
Why not?
how fast is the entire universe expanding, and so you're talking about a constant in kilometers per second per megaparsec.
Mm.
Well, think about the idea that, oh, the constellations are actually changing because the stars are moving. Yes, but all of human history. 15,000 years back, we have clay tablet records of constellations like Sagittarius and Ursa Major, Orion, and they're the same. The
Yeah.
universe is so vast that change happens over such a fantastic time scale, cosmic time scales, that we can't measure them directly. There was a big challenge to find proper motions of stars, and it took decades because stars are really far apart. And even though they're moving at tremendous velocities compared to terrestrial stuff,
Hmm.
hundreds or thousands of kilometers per second, but compared to the vast distances of the Earth, a snail is a locomotive. It's just the change is too slow for us to measure directly. The
Right.
other problem is measuring the Hubble constant depends absolutely on knowing how far away are things. Well, that's really great, but how far is up has been a question for millennia. It's been something we're just learning to grapple with. And really, it's a late 20th, early 21st century thing that we've now got good ideas. Now, Hubble had some ideas. He said, oh, the Andromeda Galaxy is about 1 million light years away. We refined that since we believe it's now about 2.5 million light years away. But pegging the distance to cosmological things is really, really difficult. And so, what we do with the Hubble constant is we measure it indirectly. We measure things that allow us to calculate what the Hubble constant is. And basically, right now, the other nice thing is that with the Hubble constant, we look and we say, aha, um, we have different ways to measure this. And this is a standard. This is a standard in science. You want to learn how fast light goes? Somebody says, I've got an experiment. I measure the speed of light as 3 million kilometers per second. And somebody else says, well, I've got a different experiment to come up with the same value. And how do we know the first value is valid and the second answer is valid? Do they both come up to the same level? Are they within the same error brackets? Right? In other words, these multiple experiments let us refine our answer if they agree. What if they don't agree? What if you did an experiment and one said, oh, well, it's 3 million meters per second for the speed of light. Another experiment said, no, it's about 3.9 million meters per second. And somebody said, no, it's about 2.2 million meters per second. At that point, you realize, well, either our apparatus is messed up, or our methodology is messed up, or we don't really understand the speed of light as well as we thought we did. And so we have today 3 very brilliant lines of research. And we're not talking about one guy, Frankenstein, in his laboratory. We're not talking about that. We're not talking about Hubble working with a couple of assistants on Mount Wilson. We're talking about teams of hundreds of people who are gathering data. And the first route is the cosmic microwave background, what we refer to as the CMB. We're gonna give you some acronyms today, folks. They're all in the show notes. So if I burble on the acronyms, please go ahead, check the show notes on me. This cosmic microwave background, keep in mind, this is what we call early universe data. The cosmic microwave background was released as soon as the universe became transparent. That's about 370,000 years after the Big Bang, which is a teeny tiny fraction of a percent of the current universe's age of 13.8 billion years ago, if you believe the Hubble constant data. The second line is a more modern line, and this has been worked on in the 21st century, and this is called the SHOES group. And that's the supernova H0 equation of state for cold dark matter. So supernova H is S, H0, H little o, and then ES for equation of state for cold dark matter. And this is modern universe stuff. This, we're looking at galaxies around us. And so the data may be from galaxies which are a few hundred million light years away. So those are really close compared to the source of the cosmic microwave background, the CMB. And the third one has just come out in the last 2 or 3 years. And this is called the TRGB, or the tip of the red giant branch. And these are very old stars in fairly close places. And so we've got 3 lines of data. The interesting thing is, big sigh, they all give us different values. And not by a little. We're talking significantly different values. And we'll get into that. So when we talk about this and the idea that we can't measure H0, that's the Hubble constant, friends, H0 directly, we do make some assumptions, and some of these are purely theoretical and some of them are based on data. The first is that the universe is isotropic and homogeneous. This basically says that the universe is the same everywhere, and the universe is the same no matter from where you observe it or in which direction you look. If you remember the line from Frank Bowman, the character in 2001, oh my God, it's full of stars. And the Hubble Deep Field photograph, they pointed at a spot that was supposed to be empty. And they gathered light for 100 hours. They found like 50,000 bazillion galaxies. And oh my God, it's full of stars. The idea is if we pointed the Hubble anywhere and we just turned the cameras on and let it collect data, we would get a similar picture. This is the idea of an
So,
isotropic
Dr. Barth,
universe.
I had the honor one time of asking Alan Sandage. He was giving a talk. I
Wow.
raised my hand. I got a question. This is why you should ask questions. Alan Sandage, he was a protege of Edwin Hubble. Okay.
He
And I
was
asked him, I
Hubble's
said,
primary student. Yes.
they had this measurement, which is different than the age of the universe now. I think it was 18
Right.
billion light years, something like that. And I said, okay, let's say that we fly. We got an amazingly fast spacecraft, and we fly to the edge of the age of the universe. I said, what do we see when I stick my head out the spacecraft? He said, everywhere that you look, you still see an 18 billion year universe, every
Yes.
direction.
Yes.
So is this
Yes.
leading into the thinking of a homogeneous universe, or is he not giving the piece of the puzzle that the universe has now expanded even further?
Well, that's the isotropic universe. No matter where you are and in which direction you look,
Yeah,
it's all the same. Homogeneous means that it's the
isotropic. Okay.
content, the galaxy density, the types of radiation, gravitational, magnetic, electric fields, all the contents of the universe. If you were to take a big enough scoop, and you have this giant, swimming pool of Rocky Road ice cream, and you take a steam shovel sized scoop from anywhere, you're going to get the same amount of marshmallows, almonds, pecans, and chocolate fudge
I
and vanilla
see.
ice cream everywhere you scoop. That's the homogeneous idea. And if you think about it, Scott, these are all extensions of the Copernican principle. Copernicus
Got
said,
it.
we're not anything special. We're not anywhere special. Every place, if your data says this only works if we're in a bubble of expansion, if we're in a bubble of highly dense matter or highly rarefied matter, basically what it amounts to, it's all the same. The Copernican principle, Copernicus advanced this idea long ago, 500 years ago, and this is kind of the modern astrophysics version of it. The isotropic
Yeah.
and homogeneous says there is nowhere special. It's all the same. The other assumption we make, and we continue to test and hammer away at this, but nobody's found a crack in the armor of this yet. We're assuming that the universe obeys general relativity theory, the GR theory, all the time, everywhere, throughout history and on into the future. That general relativity describes gravity and gravitational fields and how the universe matter interacts. John Wheeler, who is a student of Einstein, put it most succinctly. He said, space-time tells matter how to move, matter tells space-time how to curve. And therein is the core of gravitation and general relativity. My professor, Philip Marcus, in college, my astronomy professor, was a student of Dr. Wheeler. So I'm what is that, 2 degrees of
Yeah,
freedom
that's
removed
cool
from
though.
Einstein? So, yeah. The third thing is that we make the assumption that distance is always equal to the speed of light times time. Einstein said the speed of light is invariant. He indeed wanted to call it the invariance theory, not the relativity theory. And the speed of light is invariant. And so whenever you multiply the speed of light times time, you get distance, or a very good approximation of it. Gravitational fields do warp time. We know about the Lorentz equations and everything. We say, oh, well, around black holes, time is distorted. Yeah, okay. But when we're talking about vast cosmological distances, looking at distant galaxies and supernovae, we're making the assumption that distance is speed of light times time. Well, the third thing we used to think, and we no longer think this, we thought the universe was dominated by matter. Almost everything is matter, and then there's some radiation. We don't think that anymore. And this is a 21st century doctrinal change, and it's like a magnitude 9 earthquake off the shore of California. It changes everything. In the last 22 years, we've said, no, there's dark matter and dark energy, and the two of them make up 95% of the universe. Baryonic matter, the stuff that's me, you, dust, stars, plasma, 5%.
Hmm.
And so it makes you're a speck lost in the vastness. Yeah, it makes that even more profound. What we
Yes.
are is 5%. Now, I will tell you, we talk about dark matter and dark energy, and we talk about them and we say, oh, dark matter, we can't see it. It doesn't seem to interact with anything. The only way we can detect it is by gravity and gravitational effects. And so from gravitation, we're going to say, yes, it's real. The last time we had a theory like this, it was called the ether, AETHER, if you're going to Google that.
I remember
The
reading about
ether,
it.
yes, you're reading about it. The ether is the stuff, and we say, oh, light is a wave. Fine, if it's a wave, what's it waving in, right? A water wave waves in the ocean. A sound wave waves in the air. A seismic wave waves in the earth. And it waves differently when it passes through liquid and stone layers, etc. And they said, well, if light is a wave, it must be waving in something. That's the ether. And they said, well, if light has a medium, what could it be? And they had all sorts of calculations about how rigid
I
it
think
was,
we've
how
lost
thin
your
it
voice.
was.
There we go.
They had, oh, am I back now?
You're back now.
Anyway,
Yeah.
they had a great deal of theoretical calculations defining the characteristics of the ether in order to make light travel at the speed it does and the distance it does, et cetera, et cetera. And then one day somebody did a detection experiment and said, it's not there. It's the famous Michelson-Morley experiment. They said, well, if the ether fills the universe and the Earth orbits the sun, we must be moving through it. And if we're moving through it, we ought to be able to tell the difference between plowing into it, in other words, looking out the windshield, right? Or looking out the back window. If you're in a car and you look out the windscreen, you see telephone poles are coming at you. You have certain visual effects because you're driving toward things. They seem to be getting bigger. You look out the rear window, the effects are reversed. And so they said, gee, if light moves through a medium, then we ought to be able to detect a speed difference between the way the Earth is moving through space and the anti-direction that the Earth is going. And they weren't able to find anything. No matter how they arranged the experiment in any direction, in any dimension, they found no change in C and the speed of light. And so they said, I think we found something really strange.
Daniel.
This ether we've talked about for centuries doesn't exist anymore.
Daniel,
Sir.
We lost your audio once again.
Oh, golly.
Oh, now you're back.
Okay.
I still hear him on my
I'm
end,
checking.
Scott.
I show that I'm connected and secured, and I have.
The
I'm going to
audio
move
hasn't
my.
left my ears.
Oh, the audio. Oh, I see. All right.
I don't know.
Are we getting me now? Am I in?
Yes. It's great
Okay.
now.
Interesting.
So we have these assumptions and these ideas. And so if we're coming up with different values of H naught, what do they mean? Well, an H naught around 50, that is 50 kilometers per second per megaparsec. That's the expansion rate. And what that expansion rate means is it's basically a property of space-time. We talked about this raisin bread analogy last time in our last program. I'm not going to rehash that. But a value of 50 means an old, stately universe that's very slowly and gradually expanding. An H naught of 100 says we have a young, rapid, energetic, expanding universe that is blasting apart at a high rate of speed. And we've spent decades looking at the Hubble constant, and we were hoping to be able to find differences, to find changes, either changes over the decades of the survey. This is very much like the Sky Catalog survey, and we look for the changes in the position of stars to determine their proper motion. And we've also looked at different epochs in the universe by looking at different distances as we move out towards the 13.8 billion light year boundary, the farthest we can see. Well, we had an idea that if we find the Hubble constant has been slowing down over the history of the universe, this would mean a gravitationally dominated universe. It would effectively indicate a universe that should be closed, that would expand for a while and then compress again. If it was speeding up, it meant that gravity does not close the universe. And of late, we think, in fact, that we have found evidence that the Hubble constant, that the expansion of the universe is accelerating. And so gravity loses, heat death becomes the end state, but we'll go on from there a little further. So when we talk about wanting to measure H naught at different times and different epochs, we're talking about the idea, every astronomer knows this. When we look out into time, into space, we look back in time. The moon is a second and a half ago. Jupiter is about 3 hours ago. Pluto is about 12 hours ago. If we look out to Andromeda, we're looking 2 million years ago. The Orion Nebula is about 3,500 years ago, because that's how many light years away they are. Well, if we're going to measure distance accurately, Scott, we need something we call a standard candle. Here's the idea of a standard candle.
Okay.
If you have something that you know is a precise luminosity, and we use the terms luminosity and brightness interchangeably, but we're not going to today. Luminosity means how much energy is radiated out, right? How much energy does a star give out? Brightness is how bright does it appear in our telescope? And we know that as things move farther away, luminosity does not change, but apparent brightness does. If we think about an oncoming car, we know the brightness of the headlights is not changing. Nobody's turning up a little dial inside the car as it comes closer to us. The light is constant, but as it drives closer to us, it appears brighter to us. And so in astronomy, we can say that, brightness is luminosity divided by the square of the distance. Why the square of the distance? Because brightness follows the inverse square law, just like gravity, just like electric fields. Thank you, Isaac Newton. So you get twice as far away, you get 1/4 the brightness. If your standard lamp is 10 times farther away, then it's bright, and that's the inverse square law. So once we know the absolute luminosity of something precisely and accurately, then we can measure its brightness in a telescope, and we can do the math. It's quite simple. And we can say, okay, our standard candle is this far away. And we need to know how far things are away. So when we do our calculation, because calculating distance is part of the Hubble constant, it's kilometers per second per megaparsec. That last term is a distance, so fundamental to finding H naught. So what do we use for standard candles? Well, we use a number. We have 4 right now, which is amazing. We used to have 1. The original one, we talked about the women who worked as calculators for Harvard Observatory, and they discovered the relationship of Cepheid variables of brightness and period. And so, we look at these things and we can say, oh, we have Cepheid variables. And we understand the physics of why this is true, because it has to do with expansion and collapse and equilibrium states, et cetera, et cetera. But with Cepheid variables, if we can measure the period, we can precisely determine the absolute luminosity of the star. And it doesn't matter how far that star is. We can detect Cepheid variables and measure their periods in other galaxies out to about 20 or 30 million light years. So we can go quite far. Yes, it is.
Were you wanting to share your screen?
I don't have any images yet, but when I get to them, I will.
My bad. I'm sorry.
No, that's quite all right.
Maybe there was a glitch.
No. No. I'm on
Thank
it.
you.
The second one is a type 1a supernovae. And we still don't understand how these work precisely, but we basically understand what happens. We have a binary system where we have a white dwarf and a red giant star, a binary pair where one star has died before the other. As they spiral together, the white dwarf siphons and captures matter, plasma, from its giant companion. Because its giant companion is so large, it does not gravitationally bind the outer layers as strongly as a white dwarf does. So material flows over onto the smaller star, and the smaller star is dead. There's no fusion. But when you build up enough material in a shell, the
Gravity.
gravitational power of the white dwarf compresses it, and you get a supernova that goes off, and they're always the same. You can only pour so much gasoline on the heating element before it goes bang.
I see.
And this amount of plasma that's pouring on, whether it's fast or it's slow, it reaches a certain level and then boom, it goes off. And so these are standard candles. We see a type 1a supernovae, and people might come in and say, oh, they found different types of 1a supernovae. Yes, research is ongoing, but the standard 1a supernovae is indeed a standard candle. The third one is the cosmic microwave background. This is not a standard candle in the conventional sense, but from astrophysics and cosmology, we know that the universe became transparent to radiation about 370,000 years after the Big Bang. And at that point, there was a recombination of protons and electrons to make neutral atoms. And all of a sudden, light is no longer being captured. And so the light is released to fly through the universe. And this is the cosmic microwave background. Wilson and company found this in the 1960s, won a Nobel Prize for it. We've done a program on that. And the cosmic microwave background, we know how far away it is. So this is one that's weird because we don't have to know how bright to figure how far. We automatically know how far. So measuring the brightness
And
gives
was
us
that measured by the Wilkinson microscopy probe?
right, the Wilkinson anesotropic
Anesotropic.
microwave.
I always miss that part.
Right, it's the Wilkinson, it's the WMAP, the Wilkinson microwave anesotropic probe.
Right.
I believe is the full name. WMAP, all caps. And Google will get you there. And the third one is quite new. This is 2010s and on. And this is called TRGB, or the tip of the red giant branch. This is Wendy Friedman, a brilliant astrophysicist from the University of Chicago. And she has done research, and she has found out that red giants, when they have a helium flash, in other words, use up all their hydrogen, and then they undergo a collapse and they start burning helium, and there is a flash, and this is very much like a white dwarf. You reach a certain precise level, and then everything happens kind of automatically. And so they now go, oh, once we see this helium flash on a red giant, we know it's at the tip of the red giant branch of the Hertzsprung-Russell diagram, the HR diagram. And these are very old red giant stars. These are very old stars. And we can measure these in globular clusters in the Milky Way, in nearby galaxies. And they're working, they're thinking, oh, well, gee, this is one thing that the Gaia spacecraft, the survey, and the Roman telescope, and of course, the Webb will be looking for these in the coming years. And they've really expanded their data set. They've got a lot more of these, and they're hoping to get more. Mm-hmm. So we've found out in the 2000s, the universe's expansion is accelerating. This is the origin of the idea of dark energy. The idea that the universe is accelerating, is constantly moving faster, means gravity will never dominate. Gravity never wins. Eternal expansion, heat death. And when we say, oh, well, if it's speeding up, why are we speeding up? If you're on a bicycle and you're speeding up, you're either pedaling harder or you're going down a hill, right? Well, three possibilities. One, they have something called vacuum energy. This is Einstein's cosmological constant, the thing he said must be there, and then he rejected, and then he said, no, Hubble is right, it's expanding. So this says Einstein's cosmological constant, it's got to be big enough that it can make the universe expand. This is the lambda cold dark matter model. And the problem with if you take the cold dark matter model and you make predictions, you find out they're a teensy bit out of step with general relativity. They're 120 orders of magnitude off. Now, just to kind of wrap your brain around that a little bit, we've talked about million, billion, trillion, $100 bills. $1 million will fit in a gym bag or a backpack. It weighs 10 kilos. You can carry it away with you. $1 billion in $100 notes isn't a 2.5 meter cube of money that weighs 10 metric tons. And $1 trillion is an entire soccer field. Doesn't matter if you're talking European soccer or American football. It's an entire football field, end zone to end zone, sideline to sideline, filled 2.5 meters deep with money. That's 6 orders of magnitude. The lambda cold dark matter and general relativity are off by 120 orders of magnitude. 120 zeros. This is a problem, to say the least. You might as well be saying infinite. It's just so big, it just breaks my brain. You're talking a greater order of magnitude than the proton to the visible universe. It's just nuts.
Hey,
the second idea is sorry?
I said maybe you'll get lucky and arrive at the right number. But how would you ever know?
There you go. How do you know? The second idea is something called dynamic dark energy. This is the idea that it's a field, right? It's a field, like gravity, like electric field, like magnetic field. And this field is repulsive and it's pushing everything apart. Well, if it's a field, it's not a property of space-time anymore. It's in space-time, the way a magnetic field is. Also, fields can change over time. Gravitational fields do, electric fields do, magnetic fields do. And so this opens up a whole other box of worms. Maybe Hubble isn't constant if it's caused by a field. And the third one is the landmine, the third rail in the subway. Let's change general relativity. And of course, Einstein himself is famous because he was the first guy in 3.5 centuries to make a significant correction to Newton's theory of gravity. And is Einstein's general relativity the last answer? No, it breaks down around black holes and stuff, so we know it's not the be-all, end-all last answer. But if you say, oh, I've got an idea, Einstein was wrong, and I have a better idea for general relativity. I have a better theory of gravity. You know, when you say that out loud in a room full of people who know better, they know one of two possibilities. The 99.999%, you're a crank. You don't know what you're talking about. Or you may be the Swiss patent clerk, right? Submitting 4 papers in a year that changes everything. So are you a genius or are you an idiot? And it's not an evenly weighted 50-50 chance. So these are the 3 possibilities. And so let's take a look and we'll fulfill the wishes and dreams of Mr. Newton, and we'll share a screen. There we go. So what do the different data sets tell us? If there's a number of different things we're talking about here, what do they tell us? Well, we look at the cosmic microwave background, the WMAP satellite, the Wilkinson satellite. This is exquisitely precise. They've been measuring the precise temperature of the cosmic microwave background in very, very tiny fractions of a degree Kelvin, in very small fraction of an arc second areas of the sky. And their theoretical calculations, unlike the cold dark matter and general relativity, where they're off by an insane amount, these measurements we took from the Wilkinson probe agree exquisitely precisely with the lambda cold dark matter model. If you take a look at the solid red line on there, on that graph, that's what the cold dark matter model predicts. And then you take a look at the blue dots, some with error bars. This is what the various cold dark matter research people have found. And you look at the shape of the curve is not random. It's very distinct. It's very unique. And yet the data points follow it with tremendous precision. And the cold dark matter and the microwave background data give us an H0 value of 67.4 plus or minus 0.5. Now, this is basically one data set because we've only got one universe, and what we're looking at is cosmic microwave background from the universe. Now you can bring on a better instrument, but you're still looking at the same thing, right? There's no such thing as, I want 5 more universes and measure them. No. Now, you can go ahead and have 5 more surveys with a satellite and a camera system that you think is better, right? But in fact, there's only one data set. So this gives us a value of 67.4, and it's a very small error, plus or minus 0.5, which is really highly accurate. It's really highly accurate. On the other hand, we have the Cepheid SN1A data. Allow me to explain. This is data where we're looking at a Cepheid variable that's in a distant galaxy.
Okay.
And we're also finding in that galaxy a type 1A supernova, and we're using the 2 standard candles to calculate the distance to the galaxy. And so if we have 2 standard candles,
accurate, right?
Give you pretty accurate. And they have used 7 different research methods, 10 independent data sets. Many of these groups have worked independently, deliberately not talking to their colleagues, doing the same stuff. And this is the SHOES group, the supernova H0 equation of state group. And they give us an H0 value of 73.2, plus or minus. And you're like, oh, well, 67 is pretty close to 73 until you start figuring out the percentage difference. And you're like, oh, from 67 to 73, those values are off by more than 10%. In the speed of light, that's what, 300,000 meters per second difference? That's a tremendous difference.
Yeah.
Okay. And this research, one of the big guns in this area is Professor Adam Rees. And there's a link in the show notes to a really exquisite, it's about a 50-minute video. Then there's questions and answers from his audience. It was actually a webinar. But I've got a link to the YouTube video of the webinar. And he goes through, and this man, it's a tour de force. It's wonderful. And you look at his data, and at the end, you're like, oh my God, he must be right. All these data, and he talks about, he does this diagram where he shows, gee, here's the slope, and he talks about near, middle, and far distances, and they all line up very exquisitely on a line. Oh God, excuse me, guys. I have an emergency. I gotta take this. Go ahead and mute me, please.
Okay.
Yes, hi. Yes.
So with all these different values that these people are arriving at, you can tell that we're a long ways away from really understanding the Hubble constant. But you can see also at the same time that this is something we got to keep working on. Because what else do we have? So there may be some other candle of measurement that we come up with, but we'll know more, I suppose, once we get more data back from Jay West and the Nancy Roman Space Telescope. These new space telescopes may, in fact, find other ways to measure this Hubble constant. But I have a feeling that Dr. Barth is going to give us a little bit of insight as to what the next steps are going to be. And while Dr. Barth is going through this, I do want to mention that we're going to have our 97th Global Star Party tomorrow night. It is Cosmic Frontiers, and we have some new people that are going to come onto the program. One of them has been on the program before, and that's Anshul Puri, who maybe over a year ago gave a presentation on astrophotography as he was learning it. And then there is I don't want to ruin her name. Let me get it right here. Mayssa, Mayssa El Yazidi, and she is in Tunisia, Africa, and she is with the International Astronomical Union. She is the National Outreach Coordinator for the IAU in Tunisia. So that should be pretty interesting as well. Other favorite people that and regulars that come on, like Kareem Jafar and David Levy. Dave Eicher will come back to talk to us. His topic will be about sulfur minerals, and so we back, Dr. Barth?
We are.
Good.
I'm
okay.
back.
Now the question is, I was kind of alluding to, there's all these variances in trying to ascertain what the Hubble constant is.
Yes.
Is there light at the end of the tunnel? Is there are we, with Jay West and with the Nancy Roman Space Telescope, are we going to find yet another marker of distance? Is that the hope?
Indeed, we have.
Okay.
Indeed, we have.
So
and that's the tip of the red giant
I,
branch, the very old red stars. The interesting things is Wendy Friedman, University of Chicago. And these are a new standard candle, something that we've just figured out. That is a standard candle. Research is ongoing, and the data set is expanding as we speak. The interesting thing is this gives us a value of 69.8. It's measured closer to us than the Cepheid 1A and much closer to us in time and space than the microwave background. And so as we look farther out in space, we seem to be getting a larger Hubble constant. And so the question now is, does this represent real change in the Hubble constant over time? It used to be much bigger and it's slowing down. Well, that seems to contradict the idea that, the universe expansion is accelerating, or does maybe the speed of the acceleration, do we have periods of acceleration and deceleration? The way the sun has activity, high activity and low activity periods in a cycle of 22 years. And so all this interesting data. Now, the University of Chicago team are saying, ours is a really good result because we're in between the other two. And so maybe we're right. One group was too high, one group was too low. Hello, Goldilocks. We're in the middle.
And so not too cold.
The answer is, this is another one of those bleeding edge areas of science where we are actually experiencing science as it changes, as it happens, as it moves, as it grows, as we struggle to understand the data. None of this comes out of the telescope clear cut. None of this data comes off and it's clear cut. One of the things I always am suspicious of is when somebody takes a look at brand new things and says, oh, I know what that is. The latest example, Scott, the door on Mars, right?
Oh,
And
right.
you're like, right? Oh, it's a door. It was carved by ancient Martians in their, underground habitat.
I love
And
that
they
story.
left the door open when they left, or the
Of
last
course,
guy
they
died
left
and
it
didn't close the
open.
door.
Yeah, just like
And
a
yada,
bad
yada, yada. And NASA's saying,
roommate.
no,
Yeah.
hello, rock fracture. It's about as big as your computer monitor, most of you. That's about the right size for it. And
So the Martians are really short
unless the
then.
Martians were truly
Little guys,
little
okay, like
green
G.I.
men,
Joe from the 60s.
like
Yeah.
G.I. Joe size, that door isn't going to work. And so, but the immediate answer, oh, I know. The clown who says, ooh, here's new data from NASA, from Webb, from wherever. Oh, I know what that is. I know.
what it is.
No, you probably don't. It takes a lot of thought and a lot of mathematical analysis, and very brilliant people get together and hash this out. I was lucky enough to spend a number of years in a research science position, University of Illinois, working for the U.S. government, and at Caltech. I was a researcher at Caltech, very junior, very low level, not trying to grab, but I remember sitting in on these conversations. We were working with oncogenes and how genes turn cells cancerous and turn the cancer gene on and off. And we were looking at the data as it was coming out of the culture plate and hashing out. Different people had theories. And we were coming up with, well, how do you test that? Can you come up with an experiment to prove that true or false? And this dynamic process was going on day to day. The same thing is happening right now. But when you talk about something as big and complex as the entire shape, age, size, growth, and extinction of the universe, it's going to take some hashing. You think about Copernicus said, well, he understood in about 1550 that the sun was the center. And you go from that time to when was the scientific community fully convinced? Well, it was well after Galileo was dead.
Yeah.
You're talking around 1700. So about 150 years for this single fact to become an accepted concept on which other people then use to interpret their data from new explorations. So this isn't going to be settled in my lifetime or yours, but it's really exciting to watch the process. And this TRGB data stuff, this was new to me when I started researching this week's program. I'm like, oh gosh, that's awesome. Look at this new data, a new standard candle, because we haven't had a new standard candle in 20 years. And somebody says, I've got one. And you're like, wow. And their bona fides are very. Wendy Friedman is a brilliant scientist, and she's been doing work for quite a long time. And her group at the University of Chicago they have all the chops. And when they say, ooh, we've got a new standard candle, and look at our data, look at the physics, you can go, oh, all right, this analysis I trust because of all the work that went into it before, not because somebody says, I have a brilliant idea right now. And Einstein moments and people do come along. Galileo, Kepler, Newton.
That's why it's so important to encourage people from all over the planet. You do not know where the next Einstein is coming from, whether it's a he or a her, or
Einstein's family was not
live
particularly
in poverty, or were they born in wealth?
Copernicus's or Kepler's or Newton. Any of these people, Hawking, none of these people came from a distinguished line of great scientists. The only exception to the rare blossom from an ordinary meadow is really the Curie family, where he won a Nobel, she won a Nobel, their kid won a Nobel. That apple didn't roll far from the tree, said Newton.
Right.
Yeah, but that's the real exception to the rule. And even then, the grandchildren are not like that. I I think there was an ad. Oh, I think this was in the 80s or 90s, and
Hmm.
a car company hired Einstein's actual grandson to say, "Oh, this car is brilliant," when this guy was actually very average. Do you remember that ad, Scott? I think it was Buick.
No, I don't.
No?
I'm gonna have to find it
Okay,
on
guys,
YouTube.
there's your web quest for today.
Yeah,
Look
that's
up
right.
the ad featuring Einstein's either grandson or
Okay.
great grandson. I
Okay.
think it was his
Now,
grandson.
our audience did have a couple of questions here.
Yay!
I'm gonna survey again, but one of the questions is from Connor Bradley, and a bit off topic, but he wants to know, you know, how do you know about supernovas? So he said, how fast is the process of a supernova? How long does it take for the nebula to expand?
Oh, well, the nebula expands at a fraction of the speed of light. When a supernova goes off, the actual explosion takes some number of minutes, as I recall. But a supernova continues to brighten for a period of weeks, which means the explosion is still ongoing and generating more
All
energy.
right, that's true. That's true. And
You
you and
think
I
of
have
a
observed
firecracker.
supernovas in
Think
other
of the light
galaxies.
curve of a firecracker, Scott. It brightens and then dims very, very quickly, less than a second, because
Sure.
there's not much material to be consumed. If you have a big bomb, you go look at film of a nuclear weapon, and it brightens and then fades over a period of a couple of minutes. A supernova takes much longer, so the explosion, the neutrons and the gamma rays and the neutrinos particularly because they don't interact with anything, nothing slows them down. They blast out immediately in a shell, but the nebula from a supernova expands much more slowly, a couple of percent of the speed of light at most, and it slows down as it expands because oftentimes the star that supernovas often expels shells of gas, and then when the explosion hits these shells, you can look at pictures of the Crab Nebula today, and you can see that it's got ripples in it from where the expanding shell of plasma hit the shells of dust and material that were blasted off from the star before.
Right. So
So
while maybe
it's a long
the
process,
explosion, the initial explosion
some number
is
of weeks.
maybe short. I have witnessed exactly what you're talking about because we've seen supernova. There was a couple of them that we saw in M51, for example, the Whirlpool Galaxy, and they last for a surprisingly long time. You know, so
Well, 1987A, the nearest supernova to us in the last 400 years. In the Large Magellanic Cloud, if I'm right, that we have just now, the nebula has gotten thin enough, and that was 1987. So 2022 is what, the 45th anniversary, something like that? And the nebula has just now gotten thin enough that we can see light from the white dwarf star remnant. So
sure.
that'll give you an idea.
And
The Crab
you
Nebula
can
went
also
off.
measure the expansion of the Crab Nebula. We have amateur
Right.
astronomers. It was a fabulous
Chinese
time
astronomers saw that in what, 1050 something, 1020 something?
1054
Around the year 1054.
AD.
Okay. There you go.
1054
So
AD. It was recorded by the
we've been
Chinese. It
watching
was so bright
we've been
you could see it
watching
in
that
daytime.
thing for a millennia. Really?
Right. Yeah.
Probably hundreds of years. And we've seen changes in it over the hundreds of years we've been watching with telescopes.
Right.
So
Yeah, there's this. Well, I won't show it right now, but let me get to the next question here. This is Beatrice Hines. Dr. Barth, I don't understand escape velocity. Why is it called escape velocity? Could you please explain it to a noob like me?
Let's think about it this way. If you take a ball and you throw it up, right, as hard as you can, or you fire a bullet or a missile or let's say a rocket, Well, we know as we throw something up, the higher it goes, the slower it goes. Think about if it goes far enough that its velocity essentially becomes, that all the energy, all the gravitational energy is consumed, and it basically now is free of the Earth's gravitation. Well, you say, okay, if you want to go fast enough to get free of the Earth's gravitation, and there's a number of ways to think about this, but the potential energy you take, how much potential energy do you have on the Earth's surface from gravitation? You put all that into vertical motion plus friction in the atmosphere. If you can overcome all that gravitational energy, you get to a point where you're now no longer bound to the Earth. And any tiny little bit of additional energy will send you away from the Earth permanently. And the escape velocity is how fast you have to go in order to get that far ahead. Newton had a very interesting idea for escape velocity, and he said, think about a cannon on top of a hill. You fire the cannon, then it falls to the ground. If you put more gunpowder in the cannonball goes farther before it hits the ground, right? What if you had enough gunpowder so that the cannonball is falling exactly as fast as the Earth is curving away from it? And so now the cannonball stays parallel to the Earth's surface rather than curving down toward it. That
So that's
speed
kind of like being in
is
orbit.
escape velocity. Right.
I see.
And interesting, when you get to some of the smaller satellites like Ryugu, I'm probably slaughtering the name, the one that OSIRIS-REx sampled just recently, that thing has gravity that's so small that a decent high jumper could jump off. If you were on Phobos, one of the small moon of Mars, you could ride a bicycle, an Olympic cyclist could ride a bicycle off a ramp and launch themselves into orbit. Why was it possible? People said, well, the little tiny rocket landed on the moon and it got back. How could it do that when you took the great big giant Saturn V to get off the Earth? Well, the moon's gravitation is 1/6. So it took very little, and the amount of mass they pushed into lunar orbit was very small. They left most of it behind. So it didn't take much rocket power to do that. There we go. I'm hoping that helps you.
Right.
So
and let's see what
I
Go ahead.
found a headline that I don't believe is true. It's kind of a National Enquirer headline, if you ask me.
Oh boy.
Let's see here, where is it? There it is.
Yeah, I don't think so. I don't think so.
You were talking about the Martian door earlier, and I was like, oh yeah.
Martian door. And
Yeah, he's too big. He's too big to get in the Martian door. I mean, anybody can see that. So,
They installed the New York lock when Earth finds front door.
There you go.
One more question here from Connor Bradley. He said, can nebula continue to expand, or do they have a limit to grow to?
No, there's no limit to the expansion, but eventually the nebula becomes so thin that it is no more dense
no longer recognizable.
Than the interstellar medium. And at that point, it just becomes, and Connor, you need to really explode this large stellar mass quantity of material that gets blasted away, that gets incorporated in other nebula, and it becomes part of new solar systems. When we look at the Orion Nebula, that contains gas, plasma, dust, and element particles from explosions all around that area over many, many millennia. And that material has drifted in part of the stars we see formed in the Orion Nebula. When you look at the trapezium, there's really 6 stars in there, but you can easily see 4 with any telescope. Those 4 stars are incorporating material from these sorts of nebulas that have just slammed into them. And it's like a wave coming into the beach and filling your sand pail. There you go. And this material comes in and becomes part of the new star systems. We are all, as Carl Sagan, we are made of star stuff. And the heavy metals on Earth, they all come from supernovae explosions and type 1a supernovae and neutron star mergers.
Hmm. Okay,
So
maybe
there we
one
go.
last important question
Sure.
here. This is from Mike Overacker watching on YouTube. He wants to know, is chocolate fudge the dark matter we're looking for? It
No,
might be the
because it
dark matter
interacts.
I'm looking for.
It interacts with the ice cream in my bowl, therefore it cannot be that.
Right. Okay.
Anyway,
Well, I
so
think that kind of
for
wraps up our show.
yeah, for next week's show, Scott, next
Yep.
week we want to make it our audience question show, our audience participation show. It'll
Ooh,
be episode number
stump,
50. And
stump
so
Dr. Barth. Okay. And you're going to have some
you
books. We're
can,
going to have some books to give away, right?
we are going to have some books to give away. You can send questions. You can send them in to Explore Scientific. Scott will put the link up in chat. You can send them to me directly at astronomyforeducators@gmail.com. Or you can wait and sneakily join the show and stump me in a surprise attack with no forewarning at all. And I love that. But we need the audience to be fired up and participating, so we have a whole show worth of fun questions to discuss. The other thing we're going to do, my latest book, Star Mentor, Tips and Projects for the Beginner in Astronomy. That book is out now. It's available for order on Amazon and Springer. Please order the paperback copy because this is a book you're going to want to take out in the dark with you with your binoculars and telescopes. We're going to give away 3 signed copies next week. We'll decide exactly how we do that. Maybe we'll post some questions and the first correct answer in, or do a drawing from the correct answer. But I will be signing the books for you.
Nice.
So you can be in touch with me and tell me how you would like the book signed, and as long as I wouldn't be ashamed to show this to my boss or my mom, I will write anything you like in your book for you. To my dear friend, it's been fun playing in the dark with you, Daniel Barth. Sure,
That
why
could
not?
be dangerous, Doc.
Well, I often tell my students when I recruit them for my Astronomy for Educators program, it's the only class where you get to earn academic credit playing in the dark with your friends. Come join me for my next class in the fall. Somehow my classes always fill up. Yay! No, seriously, we will sign them however you wish. And I suppose if you want Scott's name in there too, he'll probably do that. He may blush and demur. I'm not sure.
Yeah. I'm not going to pretend to have the contents of all that knowledge in this little head here. So
But you are my how do you know pal and my Explore Scientific pal. So we're going to have 3 books to give away, and we will be signing them and sending them out. They're available right now on Amazon and Springer.com. I haven't gotten my author copies from Springer, but I'm assuming they will be in my mailbox one day really soon. So I'm looking forward to it as much as you are. It's been a long journey for this book, and I'm already starting on the next one. Hooray. So, Scott, I'm so excited about next week, episode 50. And
50.
I'm hoping I can join you on the next Global Star Party.
Yeah, absolutely. Absolutely.
So it's
All right.
summertime, so I can be free.
Right, it's still light out when we start Global Star Party.
It's still light out, and that means I
That's
can
right.
go jump on the binoculars
still
and
play.
telescope.
Okay. Well, Daniel, thank you so much. A very, very interesting topic, and this is definitely worth rewatching again as he went through all of that information,
Yes,
which
it's
was actually becoming a little mind-numbing for me, for sure.
a little high calorie content today. Yeah,
Okay.
this is the burger, the pizza with everything.
That's right. That's right.
All right.
Well,
everybody.
thanks again,
Thank you.
and thanks to all of our audience who was watching today. And again, watch for Global Star Party tomorrow, starting at 6 o'clock here on the channels you're watching now. Take care.
Bye bye, everybody.